So when we're looking at rotations and torques, and we're trying to find an equivalent for the masses so that you can find things like angular acceleration, not only do we have to keep track of how heavy things are, we also have to keep track of how far they are from the axis of rotation or from the pivot point. And it's this measurement of all your masses and how far they are from the pivot point that forms a quantity I known as the moment of inertia, which is required to relate things like the net torque to the angular acceleration. Now, for these moments of inertia, it actually depends on two things. So for each mass or each little bit of mass that you have relative to your center of rotation, you need to know what that mass is, and you also need to know how far it is from the pivot point squared. So if we take a look at this system, let's say we have three masses that are pretty far from the pivot point. We can calculate a moment of inertia by looking at how far each one is from the pivot point. So we'll have 1, 2, 3 different distances to go with our three different masses. So for each one of these objects that is away from our center of rotation, we will have a mass and we will have a distance that it is from the pivot point. And if our masses are point masses, we can simply take mass number 1 multiplied by r squared, number 1, mass number 2 multiplied by r squared number 2, and mass number 3 multiplied by r squared number 3. Keeping in mind that this r here is just the scalar value, or the magnitude, of how far we are from the center of rotation. Now, this type of quantity here, when you have separate masses, so we're just going to treat, our three masses here as if they're individual points or individual mass distributions from the center, works pretty well, right? So we can view all the mass for each of these little circles as being concentrated in their center. That's what's known as treating it as, or treating them as point masses, and then we can put them all together to find the total moment of inertia. That, fairly speaking, is how this is done. What is a little more complicated, though, is what happens if we have an actual three-dimensional object, like a square. Well, in this case, right, our center of mass and our pivot point would roughly be in the center. And what we would have to do is for every single little bit of mass in this entire square, we would have to repeat that calculation in which we take the mass multiplied by r squared and add them all together. What that means is for solid objects, we have to do effectively an infinite number of summations because we're going to have infinite, or an infinite number of little pieces of mass all around. Now, in mathematics, dealing with infinite quantities being added together is actually what is represented by integration, right? So we'd have to use an integral type operation, which is beyond the scope of this course. So what's important to note is that for three-dimensional objects, you're going to be provided with a table in which this type of calculation is already done for you. Right? So anytime you're going to have that, you're going to have a table. Now, for these particular tables, I'm going to use a standard one. This one is not mine. It's borrowed from the University of Texas, and it looks something like this. So right here, what you'll see are 10 individual different moments of inertia. For each one, you have a picture of it, and you will also have the equivalent formula that relates things such as the mass of the three-dimensional object and some particular measurement. What's important to note is each one of these represents a separate case. So what you need to do is you need to pick the one that most reflects the system that you're going to look at. Some popular ones that you see quite often, if you're dealing with people's limbs, like your arms and legs, the one that you will probably encounter most frequently is this one here highlighted in green, because your arm is effectively a thin rod with the pivot point being on one end about your shoulder. And the little green line in this particular picture just represents around which point are you rotating. Other things that are popular are solid spheres, because the ball joints and whatnot often work as solid spheres. So do things like proteins, atoms, and molecules. And I think these two here are probably the most common one, not this hoop about the cylindrical axis. Very rarely in biology do you see hoops present anywhere. But these two are by far the most common ones that you'll see. But all of these 10 work. They all deal with different situations, and you're free to pick whichever ones you like. But the idea is for solid objects, instead of calculating them from first principles, you're going to actually just look them up in the table. The only exception to this is if you have point masses. For these point masses, which are situations in which you can concentrate all your mass into a single spot, you can use the previously discussed equation in which you can just use mr squared. Typically speaking, how you would distinguish these cases is when you're reading your problems, pay very careful attention for words like sphere or rod. Because typically speaking, the shape, if it's important, will be explicitly mentioned so that you know that that's the kind of thing you need to look at. If words like sphere or rod, non-shape-like words, are not written for things, you may assume that they are point masses.